So, hello everyone, and welcome to another session of our With Electronic webinars. And yeah, good morning or good evening. I don't know where you are all over the world, but I'm happy to see you here and yeah, that you take part on our webinar. I'm also very happy to introduce our speakers today. Jack Peters, very welcome from our partner company NXP, and Jennifer, who will take part from With Electronic. So my name is Markus Eberle, and I will moderate this webinar today and give you just some informations. Hopefully you will not see me too much, so that means that everything goes well. So, the topic of today's webinar, I will quickly share my screen. So the topic of today's webinar is power supply efficiency improvements at low load conditions. So then just some quick informations. You will be muted during this webinar today, so this means that you cannot ask us questions, but nevertheless, you have the opportunity to ask us all your questions all over the session, and later on we have some time scheduled for a Q&A session. You see the presentation will be about in total 50 minutes, and then afterwards we have scheduled 10 minutes in addition for the Q&A. And also, if there are any questions left after the webinar, just email us at webinarteam@we-online.com, and we are happy to support you there. So I think that's everything from my side. I wish you a good webinar, and now I'm happy to give it over to Jack. So it's your stage. Have fun and enjoy our webinar.
Yeah, thank you, Markus. I will share my screen. Start at the beginning. So I'm Jack Peters. I'm working as an application engineer at NXP Semiconductors in Nijmegen in the Netherlands. I'm doing for 18 years working in the development of new controller ICs, and those controller ICs are for power supplies, and then mainly for a combination of PFC and LLC controller. And today we want to talk about the efficiency, and something which has become more important in the recent years is that the efficiency is not only a good efficiency is not only important at high load conditions of the power supply, but also at lower load conditions. And especially about that, I'm going to show you several things. So why do we need or want this? So at first, high efficiency in general. There can be several reasons why you want to have a high efficiency at a power supply. There can be rules or requirements from customers, but also rules from government. There's also a matter of competition that power supply makers compare each other, who has the best power supply, and then one of the things to look at is the efficiency. So you see here some examples of that 80 plus movement, where you can look up power supplies from power supply makers and see which one is the best. So kind of competition. And then another thing which is important is that with a higher efficiency, you can also make the power supply smaller, because the heat remaining in the power supply at a high efficiency is smaller. That means it does not need to handle a lot of heat inside, and therefore you can make it smaller. Also important, especially nowadays for environmental reasons, is that you use less energy in general. That's a thing that is often found to be very important. And another advantage is that you can also make the power supply cheaper. because when you do not need to handle so much energy or heat inside the power supply, for example, you do not need to have a heatsink anymore because the MOSFETs can, for example, handle the dissipation without a heatsink. So those can be reasons for wanting to have a high efficiency. And then when you look at what is then the situation at low load, then still rules are important because especially, and I will show it later in the next slide, from some regions in the world, there are requirements by government that in standby, for example, the power supply does not consume or the application, I should say, does not consume a lot of energy, and the power supply is playing a role in that. Then there's competition. For example, here you have something which is used in Europe, where you can compare televisions for their energy need, so how much energy they use during operation. Well, smaller is not really an issue because smaller, that only relates to if there's a lot of heat inside at a high power level. So this is not an item for low load conditions. The waste of energy, yes, it is still important, especially for the environment. So a lot of equipment is being in standby during the whole time that it's not used. And then it's good that, let's say, not so much energy is being consumed by the power supply or the application itself. And then another thing is, and that's quite an important thing for this story, is that a lot of equipment, for example, here at TV, they have become what we call smart, meaning that they do not just operate in being on or being off, but also in other use conditions. And then I use the television for an example because we all know, I think, and use televisions. So you have things like that you can, let's say, maybe have a backlight or a radio function on it where you switch off the screen and the TV is only playing radio sound. Or you can have a background recording, or the TV is updating, things like that. So, and in those operating conditions, then the TV is using much less power than when it's really switched on with the screen. And for that, it's also good to have an efficiency in those conditions because, often TV makers, they compare with each other and show that their TV consumes less power in a certain condition. So this is an example of a rule which is being used in the European community, European Union, I should say, for a standby. So this is also for TV. And then you can see there are several definitions of how much energy the TV is allowed to use. Being off, but also being in a standby mode and also in an other mode, meaning that, for example, network standby mode, when you can, when it's still connected to the network and you can switch it on and off by a network. But for all these conditions, there are requirements, and those are mandatory, meaning that you have to fulfill with your TV when you want to sell it on the European market. Yeah, and then how do we achieve a good efficiency? Well, first of all, I'm going to talk about a converter type where there is a PFC and LLC, meaning a PFC converter in combination with an LLC converter. And this is an example. So this is a 240 watt board, which gives 12 volt output and 20 amps. And you plug in the mains, and then what comes out is the 12 volt. And then for NXP, we have two popular controllers at this moment. It's a TA 2016 and 2017. And they can be used on such a board. And this is a demo board, which is an example of that. So I'm going to do the story on this topology and then zoom in into that low power condition. So looking a little bit on the schematic on what can be inside in such a system is that you have indeed the PFC stage, the LLC stage with the isolated transformer giving to the output, the 12 volt, which you saw on the pictures I just showed. And then things that can be done for extra efficiency, you can use an active bridge rectifier for the mains. And you can also use a what we call synchronous rectification, but is in fact also a active MOSFET circuit for rectifying. And with that kind of improvements, you can get a high efficiency. So I'm also showing this on this slide. So often when you are wanting to improve the efficiency or to have the highest efficiency for high load conditions, meaning at 240 watt or maybe at 200 watt or 150 watt, then often a good way to do that is to replace diode rectifiers by a MOSFET, because then the voltage drop, which is normally there on a diode, will be reduced because you use a MOSFET, and then the voltage drop is much less. So current times voltage is of course the power which remains in the device, and with using a MOSFET the power is less. So synchronous rectification or active bridge rectifier is a good way to easily improve the efficiency at high loads, because then the currents are quite high, so you gain a lot. And then we have the situation at low load conditions. Well, in low load conditions, the main method of improving the efficiency at low load is to use burst mode operation. That means that the converter is not switching continuously. So this is just showing switching signals continuously, but you switch only during a short period, then you stop switching, then you start switching again, you stop switching. And the lower amount of energy that you need, you can concentrate in a small part. That means basically that in this period when you are not switching, you also do not have switching losses, mean losses of the converter working, you don't have them. So you concentrate everything in what we call bursts. So short periods of transferring energy. And just as an example on how much you can gain, and this is of course an example which is quite clearly showing it, is when you look at an LLC converter, then usually let's say the property of the LLC converter is that there are some quite a lot of losses just by having the converter running. So when it's switching, you already have some magnetic losses, the transformer being active, and those losses are present at all load conditions. So when you have a high load, then the conversion itself is very efficient. So you get some extra losses because of the conversion. But when you go to low load conditions, then these basic losses, they remain. So they are quite high. So this is just an example value. So you could end up, when you do not deliver power, that still the converter itself is using 2 watts just by running. And when you go into a burst mode, you can reduce that a lot because you only switch sometimes, and then you can reduce it to, for example, something like 70 milliwatt. So that's a big reduction. And like I said, in fact, the burst mode is that you do not have those switching or magnetic losses when you are not switching. So that gives the big improvement. So yeah, this is just a little bit a marketing picture to show that NXP has a special way of operating the LLC controller. We are using what we call VCAP control. That's a different way of the traditional frequency control method of controlling the power in an LLC converter. And there you can gain quite some efficiency, especially at low load conditions, because that VCAP control can very precisely control the moments of switching. So you can manipulate in such a way the switching that you get the best efficiency also in burst mode operation. Just as an example of kind of a result, this is one of the latest boards that we made. There you can see an example of the efficiency. Here is the output power, and here the efficiency. Then you can see at the highest output powers, higher output powers, you can reach efficiencies like, let's say, 93%. And when you go to lower efficiencies, then, a lower power output, then your efficiency is going down somewhat. But here, this is zoom out of this very last part. So going from 10 watt to 0 watt, then you can see that still at those very low power conditions, the efficiency is remaining something like 85%, meaning that, yeah, let's say all across the power range, you have a quite good efficiency. Yeah, of course, because we talk about efficiency, this curve has to go to 0 because of the way how you calculate it, but it means that the efficiency is also quite good at a low output power level. Yeah, that sounds very nice, but are there also side effects of doing it like that? Yes, there are. So there are a few unwanted side effects, especially because of that burst mode operation. So the burst mode operation, it's very good for the efficiency, for improving the efficiency at low load conditions. So that works quite well. But the side effect is that this transformer can also make noise, meaning it starts working as a loudspeaker. And how does that work is because you transfer through the transformer those blocks of energy in a certain repetition, and that kind of starts making a noise, like you have. I can try to imitate it, or some kind of effect like that, because those blocks are repeating itself. And they are repeating itself at a very low frequency, so that does not really make the noise, because this, you could say transformer as a loudspeaker cannot make very low frequency sounds, but it starts making sound at the harmonics of that lower frequency. And this is just an example of when you measure the noise across the frequency range to 20 kilohertz, then you can see most noise is being generated like 10, 12, 13 kilohertz. This is a typical spectrum of noise that you can expect during burst mode operation. But we can do something about that. So there's also a way to reduce that noise, to at least make it, try to make it acceptable. So it will always make some noise, but when the noise level is quite low, so that you cannot really hear it, then it's okay. And one way to do is that you do not make those blocks of current pulses going to the output. These are the LLC current pulses going to an output. Then you can make them, let's say, not really like a block, but start them with a lower amplitude and then increasing, and also stopping with a lower amplitude. And we call that soft start and soft stop. And by doing that, that impulse that triggers that noise it's being softened. So that's how you can do it. And there's a few other things that you can also improve it, and I will show it later. Then another side effect is that because you transfer the energy in bursts, so energy to the output and then no energy to the output, energy to the output, then you will see that your output voltage will also start increasing during the bursts, but decreasing during the period that it's not switching, meaning you have a higher output voltage ripple. So these are examples. So then you have maybe 12 volt and then 300 millivolt on ripple during burst mode. When you choose, for example, a different repetition frequency, then your ripple is smaller. And here you can see a kind of, what you could say, a load sweep. So from left to right, here the output current is 0, then you increase it to maybe the maximum, going back, then you are at 0, and then you can monitor all the behaviors. And you maybe already see here a little bit that in our controls we have several operating modes trying to get the best result at each load condition. And when you look at the output voltage ripple, you can see it here. So then you see during those burst mode operation, your output voltage ripple is usually highest. So it's higher than what you have in normal working condition. Okay, when it's very important to you, you can do something about it. So you can select an operation which has a lower ripple. But that's a kind of trade-off you can make. And that's the thing I like to show in the rest of my presentation, because yes, there's always a kind of trade-off you have to make when you want to have a good performance at low load conditions. So you're going to use burst mode operation. And then there are some disadvantages. So you have to make a kind of trade-off between how good the efficiency will be and how many of the side effects you can allow. I think usually you can get to a good result, but yeah, it's a little bit depending on the application on what's the optimum. And yeah, those controllers, and I'm going to use the example of the TA 2016, which we have already for quite some years. And with those controllers, you can instruct the controller how to behave. So that means inside the controllers, there's a memory. We call it MTP, multi-time programming. You can change it quite often to find the best result, and then go into production with the settings of the best results. So you can make settings during development with a computer connected to the IC via a I2C USB I2C interface. So here you can see it. You can make a setup with your computer, connect a USB cable, use our interface, and then connect it to the board, in fact, to the pins of the IC. And while it's running, you can make changes. So we have some software that you can use on your computer. Then you can change settings, like in the burst mode, what is the burst mode transition level? So at what power level are you going into burst mode, or what will be the energy in the burst mode? You can also select that. And then you can see the result and yeah, let's say play with it to get the optimum for your application. And how to do that, I am going to show you in a moment, because I have prepared a demonstration while I recorded it with a video in the lab. Then you can see how that works, and yeah, that's interesting to see, but also to see how the improvements, let's say, work out, what you can expect on what improvements you can reach with selections of how the burst mode should work, or optimize for the output voltage ripple, things like that. So the video is going to show the PFC and the LLC converter in burst mode operation. It will also show the PFC soft start and soft stopped, and also of the LLC. Then the PFC switching frequency, how it let's say has an effect on the efficiency, especially. Then the transition level of going into burst mode, and especially the energy which is in that burst mode, because that's also has a relation to the efficiency, but also on audible noise. And also the way how the burst mode is being made. So it's a selection of pulses, and there you can also make some choices and see the result on efficiency and ripple. Of course, there are also other possibilities to improve, but these are the things I'm going to show in the, let's say, recorded lab demonstration. Okay, and then Marcus, maybe you can take over and show the video.
At 0.5 amp output.
Maybe you can start it from the beginning. Yeah.
This is a movie about the DAA 2016 parameters that can be used to increase the efficiency at low load conditions. So the system is now running in burst mode at 0.5 amp output, and we can see here on the oscilloscope the PFC bursting, the LLC bursting on the R bridge node, and these are the currents to the output of the LLC. This is the output voltage ripple that we can also monitor. And here on the screen I have a small presentation in two parts showing the parameters that are relevant for improving efficiency at low load conditions. Normally it's burst mode conditions. And I'm going to go to show several of them that they have an effect on the efficiency, and the efficiency we can see here by the input power on the mains. So the output power stays the same, and the input power we can increase or decrease by changing the settings. So when we go to the settings overview, we have the PFC, and here that condition of bursting of the PFC is synchronously. We can change that also to have a ripple, but then we have to measure the input power for a longer time, and it's not so convenient to do that in a short movie, so I will skip that. And then we can show the effect of the soft start of soft stop of the PFC. Now each time the PFC starts and stops, there is a soft stop to reduce audible noise, but this costs some energy and will reduce the efficiency. So when we switch it off, oh, I have to do it like that. So both off, then we can monitor the input power taken from it, and then you can see that when we switch off the soft start and soft stop, the input power reduces a bit. So that means that it's good for audible noise, but less good for the efficiency. Okay, then the other thing that can influence the efficiency is the frequency limit. So the frequency limit, when you limit it, it increases the efficiency. So in this case, we have let's say a better result, but when I put it to 500 kilohertz, that's almost unlimited, or at least the limit is very high. Then you can see that the input power increases a little. So limiting the frequency of the PFC converter, that helps to improve the efficiency. The disadvantage of that is that, for example, performance like power factor or THD, they are reduced. Going back to the presentation, so from the PFC to the LLC parameters that are relevant, then we are going to look at the low power to burst mode transition. So when I change that from 10% to, for example, 5%, then it will reduce, it will increase the energy consumption, so it will reduce the efficiency. So it becomes much higher, and the reason for that is that, okay, now also the PFC get out of burst mode, it's just by coincidence, is that the energy per cycle, it becomes less. So that means that there are more cycles needed to give the same energy, and that's less good for the efficiency. So when going back to 10, you can see that this amplitude increased, and also less cycles are needed. Then the efficiency became better, I mean the power consumption became less, and I can improve it by, for example, using the transition level, putting the transition level on 20%. Then we can further reduce the power consumption, as you can see it here. That makes a big difference. There is also the energy per cycle increase. Yeah, the same effect we can also do by keeping the same transition level at for the burst mode, but increasing it via another function. That's the energy per cycle increase. So when we increase it by 4, for example, then you can also see the effect on reducing the power, and you see a similar effect here. But then the transition level going to burst mode, that stay the same because that we did not change. Okay, putting it back. Then we can also change the frequency by the low power mode. Changing the low power mode, meaning the number of peaks that are skipped before the next cycle starts. So when I put a higher amount of number of peaks here, then you can see that the efficiency also became better, because there is again more energy in one cycle. You can do it again, maybe put it to 8, for example. Then it will further increase, and the increase of the energy per cycle is a consequence of the longer time of not switching, to compensate for that. So that can be used also for that. And then we have this, we already have. Yeah, the minimum number of cycles, that's not so convenient because we have to go to lower power here. But we can see the effect of the soft start and soft stop of the LLC. Now there's no soft start and soft stop. So all the measurements we did are without it. But when I activate it, and for example put it on 4 cycles for the start and the stop, and I activate it, you can see that the efficiency becomes less. So it increases a few 200 milliwatt. Okay, now it's put on 4, so you can better, if you take 2 cycles, the effect on audible noise is also quite good, in fact maybe equally good. And then you see it becomes a little bit better again. Okay, switching it off, of course, gives the best result. Because the soft start and soft stop, they just add cycles to make that soft effect. But those cycles, they hardly produce energy to the output, so then the currents to the output are low. That means you are switching without generating much output power, and that's not so efficient. Okay, now we got an overview a little bit, very quickly, on several functions that can be used for increasing the efficiency.
Yes, that's also the end of my presentation. So I would like to hand over to Jennifer, who will continue showing things on the transformers.
Now, do you hear me? Yes, I don't have my camera on. However, I will start sharing now the presentation. So thank you, Jack. I will, yeah, now I think that I'm sharing my screen. So let's first start. So my name is Jennifer Guerrero. I'm a product definition engineer for custom magnetics at World Electronics. And obviously now we're going to be focusing more into the part of our components, such the part of LLC transformer and PFC chokes. So this presentation was done jointly with our colleague Jared, who is going to be presenting in the afternoon. So let's now go to what we're going to be talking. So in the first part, just let me put my laser point. So yeah, in the first part, we're going to be covering like some strategies to enhance the efficiency of the LLC transformer. While everyone would like to have like a perfect solution and have the unique solution for optimizing the efficiency of the transformer, is not the case. But we want to, with this presentation, what we want to do is give you some strategy or like less evident tactics that can help you improve the LLC transformer, where, for example, we're going to be discussing three parameters that we can influence. The first one will be gain and inductance ratio, then the leakage inductance balance, and then, as most of everyone knows, is into the part of wire selection. So let's begin with the first topic. Some of you maybe don't know what is gain or may wonder why gain is significant. So in LLC circuit, gain is the factor that when we cause, or well, it's the cause that the output voltage vary from the expected value. So based, for example, on just the trans ratio, let's say, for example, when we have that, also it can change into frequency, and it depends also on the load, as you see here in the image in the right. So to understand, for example, the impact of gain, just let's say an example. Let's imagine a half bridge LLC circuit, let's say with an input voltage of 400 volts, and yes, and let's say that it's a primary to secondary of 20:1. And with the most basic calculation, when we have would be like 400 divided by 2 multiplied by 20, it will be 10 volts of output voltage. However, if you know this is not the reality, we will have some change into the output voltage. And that is related also to the gain. So when we are, for example, now, let's check that at the resonant frequency of 100 kilohertz, and you expect it here, you see that the gain can be around 1.25. What will we have? It will be that it will elevate our actual output voltage from 10 volts to 12.5 volts. So to modify this actual voltage that we want or we desire, the thing that we can almost do is adjust the switching frequency into a lower or higher frequency to adjust our real output voltage that we want to obtain. So, but now let's delve how these principles affect the efficiency of the transformer within the LLC circuit. So as the LL circuit, it's for operating over a wide range of input and output voltage. We want to achieve this desired range, and it will be dependent also in how they're utilizing like a higher gain. So to enhance this gain in the transformer, we also need to decrease the inductance ratio, which is denoted here in M, which also will be depending of the primary inductance and to the leakage inductance. So if we want to modify, for example, the inductance ratio, it will be coming to a trade-off. So it will also impact efficiency. But let's say that we're going to be reducing the primary inductance. The thing that we will have, it will be an upsurge in the circulating current, which will be counterproductive to our system. But now let's see, for example, if we're going to be, or we want to increase the leakage inductance to improve the gain, it will be affecting the coupling of the transformer, which also going to be affecting the efficiency. So some of the simple solutions, or something that it's that we can say for having a better transformer operation, it will be also really advisable when they're designing the LLC circuit is that we should have the narrowest feasible range of input and output voltage. This also will be simplifying the design and also will help you the transformer to have a better efficiency and performance into the circuit. So now for the second topic, we are going to be focusing in the part of leakage balance. And I guess that some of you, why or what is exactly leakage inductance balance? But first, it's important to understand how this leakage inductance is typically measured. So this is usually something important for the transformers of LLC because it uses the leakage inductance as a resonant inductor, and it's characterized by splitting the secondary winding. So most of these LLC transformers are designed in the way that the leakage balance will be critical. So when we are calculating the leakage balance in a transformer, usually it's estimated by short-circuiting all the output windings, yeah? But I think that maybe you or some of you knows that it could be inaccurate because maybe we have different type of conductors inside the secondary winding and it will have a different leakage inductance depending on the conductor to the primary winding. So what will be the outcome, for example, now if we are like taking or shortening just one by one each winding or auxiliary winding and leaving the other ones open, is that we will have different values of leakage inductance. And this discrepancy will lead to an imbalance in the output current. Like that, we also will be affecting the efficiency of the transformer. So for a more visualizing thing of how the leakage balance is influenced. So as you see here, we have different distinction position of each conductor. It will be occupying into the secondary winding. As a result, each conductor interacts differently with the primary winding. And this will be leading to an imbalance. And that is also because we have an imbalance in the coupling efficiency. So let's see here in more specific in the section cross of the LLC transformer. In this transformer, we have each half of the secondary winding has 9 turns and is denoted by 2 different colors. So we have the blue one and the yellow one. But even though these ones are wounded by filigree, so this means that side by side, you can see that the yellow conductors are on average positioned a little bit further away from the primary compared to the blue ones. So what you can infer here is that this means that the blue conductors will have a better magnetic coupling with the primary one. And consequently, we will have a leakage inductance associated with the blue winding will be lower. So in order to mitigate this type of imbalance, we can employ some strategies. The engineers or the manufacturing processes can have to have a better uniform distribution, can have different type of windings. Maybe we can also physical position the windings to promote equal coupling with the primary winding. And also it can be involving some adjustment in the precision of the manufacturing processes. But in the next slide, I will also talk about the different winding that will help to mitigate a little bit this leakage, this leakage balance. So in this instance, we will be using a split bifailure winding method. The ones who are not well known about this involves winding each secondary coil within 2 conductors that runs parallel to each other. So we will have half of the cross section more equalized compared to with the primary one. And what we have in here is that we will be mitigating or we will be balancing the leakage inductance here. Why? Because we have a more uniform distribution. So that is why we are going to be enhancing the leakage balance. And with this winding technique, we will be also helping to decrease the AC losses, also owning less proximity effect and skin effect, and also we will be having a more optimized efficiency for the transformer. An additional effect here, or something that also can help to mitigate this unbalance of the leakage inductance, we will have, or what you see here, for example, the core it has an air gap and is directly positioning into the center flange of the winding. And this can be beneficial because it will help to diminish the interaction between the fringing magnetic flux and the winding conductors. So this interaction, just that I mentioned, can lead to the creation of eddy currents within the conductors. And sometimes we will, well, because of these eddy currents, we will be having a lower efficiency, but also, like, for example, in the worst case scenario, we can have that these eddy currents will be creating an amount of heat that it will damage the insulation, and it will also cause an internal short circuit in the windings. So it's always recommended, and if it is possible, to maintain a small air gap here and position it beneath the winding center flange when possible. And as a lot of you also know, that the wire selection is also influencing a lot of how we can mitigate or we can optimize the efficiency of the transformer. So it's common knowledge that the ones who are designing this, we are using, or like they are using Leeds wire at higher frequency to avoid skin depth problems, but also not that. If with more experience of a design engineer, or the ones who are always doing in the part of the production and manufacturability of the samples, they're always, because of the experience, they want to enhance the efficiency of the LCC transformer. So in the system, for example, when we have a power of, let's say, 100 watts. So let's take 100 kilohertz of frequency as an example, and we do like a calculation for knowing which will be the skin depth that it might lead. So the engineer will have a select wire of 25 AWG, yeah? But with experience, they have known that it's better to have a 38 WG Leeds wire, because it will help you to increase the efficiency for this kind of application. And also because it will let you to diminish other kind of problems that you will be having, and not just because of the skin effect. So to sum up here of the first part of the presentation, it will be, as you know, that is not really just having a unique solution. There is many articles that promote different windings and construction methods to enhance the efficiency, but there is no universal solution. So it's always really nice to work with someone that has an IT supplier that is willing to open to experiment during this prototype phase, and that is not afraid to try different techniques. So now I want just to give you an overview of one of the PFCs that we also use in the TA 2016 of NXP. So I will first gonna be giving you an overview of our traditional bobbin PFC series. We will be discussing their characteristic, the impact of choosing the right package and wire, and we're also gonna be presenting our new, well, our toroidal PFC choke series. So let's say now that we have the World Electronic Traditional Bobbin PFC series. So when we're selecting these are optimal for high efficiency. It also has the characteristic with good EMC behavior. It's always a top choice when we have also different versatility of designs. We have also some packages that it has height as low as 13.1, which is also something good for a small footprint without sacrificing the performance. So these inductors are suited for the application that we have for isolation voltage that are required for 1.5 kilowatts. And also when we have, for example, the parental range temperature of -40 degrees to 125 degrees. And when we are designing, we need a lot of different electrical parameters, but the critical ones that also are gonna be defining our component will be when we have the certain inductance, the peak current, the RMS current, the mode of operation, if it is CCM, DCM, and the switching frequency. So applications that we can use, for example, with these bobbins are, as already mentioned before by my colleague, power factor corrections. It can be also used for lighting applications, switching mode power supplies for 75 to 250 watts, and mode of operations like such as DCM. So now I want to talk about different packages that we have in our traditional bobbins, and then which would be like the influence or what can be benefit for using an RM series compared to an AFT series. So let's discuss with the RMC series. This is more into a small footprint with an excellent EMC behavior because it's shielded and have a ground core. Then we also have, on the majority of the time when we are designing this kind of PFC, we are using Leeds wire to minimize the AC losses. And then if we are going to be using EFD, it will be more into a flat design where we have application where we have a requirement of load profile. And also when we have wanted to have low AC losses, they are also use the beneficial of the Leeds wire. And when we have a PQ package, one of the main instructions is the power density, and it also provides some MEA solutions or protections, where the EE, I think that everyone is really well known about it, is the most common package using the magnetics. So it's really good all purpose, where we can have that it has that, like the most important thing here is that also we have a larger winding area, so, and it's also easy for manufacturing. So that is why a lot of designs can be used with the EE, and it's more feasible for manufacturing. So now, as I mentioned, and we mentioned a little bit in the first part of the presentation, will be the different use of wires and how it's maybe different, the beneficial between using it in our PFCs. So let's start with the round wire. In the round wire is, as we have it, we have a smaller surface area, and we are, because of this small surface area, what we are doing is increasing also the resistance AC and DC. So because also this shape, it will lead for a more higher proximate effect and skin effect compared to the other wires. Maybe I think that it's better to explain to you if some of you doesn't know what it is, a skin effect or proximity effect. So a skin effect, it's when, for example, the AC current has the tendency to go into the concentrates toward the outside of the conductor, and it's caused because of its magnetic field. However, when we have the proximity effect, I just want to clarify that everything is here because it's influenced because of also the frequency. So when we have also the proximity effect is when we have two conductors, and these conductors is caused when they are really close between each other. The distribution of the current in each conductor is affected because of the varying of the magnetic field that it causes between each other. So let's say like it's like a polarization. So it will not be using uniformly all the conductor, and it will be affecting our efficiency of the transformer or the PFCs. So for that, let's go now to the flat wire. If we are gonna be talking about the flat wire, what we have is a significantly reduced the RAC and RDC losses, and also because we have also a little less proximity effect and skin effect. Also, it depends, for example, if we have, depends on the winding style. What I mean of this winding style is that if, for example, there is a gap that is present between the wires, these induce currents from the adjacent turns that are reduced, and there is, because there is a distance between the turns, it will be diminished the magnetic field, which it also mitigates the proximity effect. So for the characteristics optimal for applications that, as I mentioned to you, when there is a higher efficiency, like higher frequency, and it also when we need to have higher withstand of high current. When we have now for the Leeds wire, it's really optimal because also we have that each strain is insulated. So it will substantially lower the RAC, along that also how the waving pattern it is. So what I mean with the waving pattern is that each strand sits on the conductor exteriors and it's distributed currently among each strand. When this is why we are distributing the current uniformly for each strand, this is advantage for high frequency applications. And also we have a diminution of the proximity effect and the skin effect because of the insulation of each strand. Then I will be just showing you briefly what we have as our new parts of series of the PFC toroidal. This is our new addition of our PFCs. So this series has a range of inductance between 120 to 720 microhenry. and it accommodates applications that require high voltage of 1000 volts DC, and it has been engineered to handle high saturations that can reach out of 105 amperes, while we have to ensure like the width of operation from minus 40 degrees to 150 degrees. And also one of the ideas here was to present different availabilities for different application where it can adjust for different kind of height and size. So we have also from 53 to 99 millimeters of diameter, and from height we have 28 to 62. And something really important for this new series that we have added is that we have low intra-winding capacitance, which also effectively we are minimizing the skin effect, we are lowering also the DCR, and something really is that it will have a lot of mechanical stability. It's really useful for applications that we have for vibrational when it's involved. And this also, some of the applications that we have been using or the engineers have been using in the part of external EV chargers, solar inverters, telecom. So now I want to show you some of the results that we have obtained when we are using this kind of PFC toroidal, where it has been having an improved cooling. So let's first dive on why first. So if we're lowering the DCR, we're directly minimizing the power loss, which in turn reduces the heat generated within the inductor. So it's not about energy efficiency, but it's also about enhancing the span life of the part. It's also having a component that is reliable, and it can mitigate the thermal stress from the component, or it can help to improve also the thermal into the other components of the board. So how we are achieving this? One, it's because we are using the flat wire design compared to the round wire. It will increase the surface, because we have a flat wire, we are increasing the surface area, and it will dissipate the heat more efficiently. It will contribute to a lower temperature rise even under high current conditions. So let's see it better with some of the results that we have in the data in the table. So for this data, we use the standard flat wire part number, and then we have also a hand wound similar round wire sample. The two has a similar core, and it was having the same number of turns to have a comparison for having the same results. So with the same, we have an inductance of around 200 microhenry. And as you see here, the flat wire, what we obtain is that the DCR is lower than the one of the round wire, whereas you see the maximum or the optimal thing that we have here is a really low interwinding capacitance and a little bit more of enhancing the rated current. And the interesting part is what we are having here is the temperature raise. You see, we have a more thermal stability when we are doing or when we are a performance with a flat wire compared to a round wire. So thank you, everyone. I think that now we have a few minutes to answer some questions. So Marcus, I will let you on with the presentation. And yeah, thank you, everyone. Marcus, we don't hear you.
Okay. The problem stands before the system. Sorry. So yeah, I was just muted. Thank you very much, Jennifer, and also Jack. Thank you. And yeah, so you see, we are a little bit over time, but we have still the time for your questions. We can see there are a lot of questions coming in, and yeah, you can just the information, you can just type them into the chat. And yeah, we will answer them live. And if we can't answer all your questions now in the live session, we will answer them later on via email. So yeah, so don't lose any more time. I would start with some questions. Yeah, we have usual questions also from other sessions with this topic. And yeah, I would like to start with that. So first question, Jack, to you. How do you measure audible noise?
Yeah, the audible noise. That's one of the things I talked about. Maybe I can share something. Let me see. Share my screen. Share. No, this is not the one I wanted to share. Sorry.
Hmm. No problem. Okay, by the way, I also see the question, could we have the presentation files? Yeah, so you will get afterwards, after the whole session, we will send you the link to the recording of the session as well as to the presentation. So you will get all links from us.
Yeah, sorry, I have some problems of showing the presentation. I don't know why. I will start it again. Maybe I can do first another question.
Yeah, so then we will hop on until you try to connect it. So then the question would go to Jennifer. Could you explain how the split bifilar winding method contributes to achieving a more uniform magnetic field distribution in LLC transformers?
Great question. So I think that I have mentioned it before in my presentation. So when we are involving the winding of each half of the secondary coil within 2 tiners of the coil, or like of the conductors, they run parallel. So when we have a cross section upper to the other one, we have the balance of between these coils of the secondary winding. We'll be able to have a balance of comparing or like interaction with the primary winding. So instead of having one like this and one like this, that there is a distance between them, it will be enhancing, rather when we are having here, it will be enhancing the interaction between the primary winding. So it will be balanced the magnetic interaction between them.
Okay, thank you very much, Jennifer. So then, Jack, question to you. Are you ready now or?
Yes, I think I am.
Okay.
I'm sharing it, I think, now.
Then
so, measuring audible noise. You can make a setup like this. This is the one we are using. So it's a kind of box. Control L. Like where the sound is being absorbed. So it's a box of 1 square meter about. And then you put the power supply here and the microphone. You can see it here on top at a certain distance. And then, usually for the experts of measuring sound, it should be 30 centimeters, because then you don't have any near field effects, as they call it. But customers often use it very close to the power supply to have a good measurement result, that you have let's say, can measure the sound more clearly. And for that, we use a setup here in Nijmegen from Buell and Kier. It's just a microphone with a setup that we can connect to a computer. And then we get these kind of graphs on the computer. So you see the frequency range, and at each section you see a bar of the noise level. And it looks a little bit like this. So when you measure something, those bars, they move constantly, and you can check the maximum level that you want to measure. Here is a setup where we make that such a load sweep, and you can go through the whole load and see where the maximum noise is happening. So in that way you can, let's say, real time observe where the maximum noise level is. Usually I already indicated during my presentation that it's in the burst mode, especially for the LLC converter that makes most noise of the burst motor, but this is the setup that you can use.
Okay, so thank you very much, Jack. So then we would go on with the next question. So it was a general question, and I think also the other attendees answered it in the meantime. So I will just post this question. So what does PFC and LLC mean? So I will just go into the chat and read the answers out from our attendees. So PFC is power factor correction, and LLC is Okay, it's an explanation. It's is a resonance switching topology. Maybe you can also give a little background on that question.
Yeah, so the PFC, it's a circuit which is required by legislation when you have a power supply for high power level, so above 75 watt. It's a little bit depending on what type of application you have, but usually it's required. And what it does, it makes the current taken from the mains look like a sine wave current, so that the load to the power plants are nicely distributed in time and not only transferring the energy to the peak. So it makes a kind of sine wave current taken from the mains. That's the purpose of that power correction, of a power factor correction circuit. That's also in the name. And the LLC, it's a resonant topology indeed, and the LLC name stands for the components being used. And I think I showed it also a little bit. I can also show it again in my presentation, because I also copied it a little bit. Here you can see that. So here you can see a schematic diagram of an LLC converter. And then, maybe on this side, so here you have a half bridge construction. So you have a DC input voltage of 400 volt, two MOSFETs that switch to 400 volt or to 0 volt, alternatingly. And then here you have an LLC construction, and this gives a kind of resonance that you use for controlling the power. And what Jennifer also was talking about, you can, those components, especially those inductors, that two L's, you can make a transformer that already has these properties, meaning that your leakage self-inductance is standing for one of the inductors that is needed to make this circuit work. So sometimes when you use a transformer construction which does not have a big leakage, then you can add a separate coil to have a leakage function. Inductor function. So then you also have an LLC, but in principle LLC stands for those components. You also have resonant converters which have a different construction, but we use the LLC a lot because it has a very high efficiency at high loads. That's the main reason, and that's why it's also so popular nowadays, especially for the larger power applications. Then most applications use an LLC resonant converter because of the high efficiency. Then you can make things smaller or have cheaper or things like that.
Okay, Jack, thank you very much for the answer. So then I would just hop on to the next question. So yeah, my question is a bit off topic, but I'm keen of hearing an expert input. So on flightback transformer, we found better efficiency on some designs if the primary winding is split into an inner and outer, for example, the secondary between. We assume it has to do with less stray inductance. Why is this not a common practice? So this is the question.
Okay, I think that I can somehow answer it right now, just briefly. So when we are splitting this primary winding and we have in the inner the secondary winding, what we do is having like a chill effect. So we are having like this kind, it will be creating an effect like a shielding that we're doing for a transformer, and it will help to improve the efficiency. Why sometimes it's not a common practice, as I think that someone answered it, is that because of manufacturing processes, it will be adding cost to the system. So sometimes when the cost is one of the trade-off, it will be not performant. But when something that is really high performance and we like to have a better efficiency, we will be doing this, but the cost will be a little bit higher.
Okay, Jennifer, thank you very much for the answer. So then we would hop on to the next one. So the question is, does operating in burst mode reduce the lifespan of the involved components?
No, No, because very simply said, the power levels where you use the burst mode are very low. That means that during that period that it's switching, the energy is usually much lower than when you operate at high load. So then the stress is also less. So for the components, it's not really having an effect on lifetime. Even the lifetime is longer. Of course, one thing that you have to keep in mind is that when you are in standby, you're maybe on for a long time. Meaning, of course, the time that you use the power supply, it's longer. Although the stress is less, the time is longer. So that's one thing to consider. But usually, because the power levels are so low, it does not really have an effect on the lifetime. But I don't know, maybe Jennifer, you have an opinion on that, but that's what I understood, at least from transformer point of view, but also from MOSFETs. Well, one thing that is important is, of course, that the way how the switches behave should be, of course, normal and properly, because what you saw, what I presented, is that you are in burst mode manipulating a lot during the switching to get a soft start, soft stop, all those kind of things. And of course, that should be done well. So normally, that's working fine. But you must make sure of that you do not have, let's say, something like bad switching, because that could, of course, have some effect. But when checking everything and the working is, it should have no effect on lifetime. Yeah, that's the answer.
Okay. So thank you very much, Jack. So then I think we have time for one more question. Yeah, as already said, the open questions, we will answer them later on via email. So I would probably go for that question. Proximity effect can be solved by twisted of wires, right? So how the proximity effect is reduced if wire strands are separated by insulation, she mentioned in the table. So maybe this question was referring to the video we saw.
I can also maybe answer this part of the wire. So when we have insulations between each strand, and because we are twisting it in the wave, so it's called the waving pattern. When it's twisted in the way, the current it's uniformly distributed for each strand. So everything is for each strand there is a unification between the influence between each strand within all the leads wire. So the waving pattern is how it's helping to diminish the skin effect. So I don't know if I can explain it better, but maybe I can answer it more into one-to-one. I can answer it afterwards, but this is just, I think that we're running time, but that's just a small explanation.
Okay, so thank you very much, both of you. And so that is it. That was the webinar today. And I hope you stay tuned with our other webinars. Also, if you have any other questions left, just contact us. I've just uploaded here the email. Hopefully it will work for you. Otherwise, it's just the email webinarteam@we-online.com. So thank you very much, Jack and Jennifer, for your time today. It was a pleasure to do the webinar with you. And to all attendees, thank you for listening. Thank you for your time. Have a good day. Bye.
Bye-bye.